How you doing, my adopted class? I am so glad you're here. 8:30 in the morning, bright and early, ready to do math. Yay! So today we're going to pick up where we sort of petered out there on Tuesday. We're going to pick up on trig compositions. Now, trig compositions are, by and large, like any other composition, like the ones you played in 1073. There's one or two changes, and we'll get to those as we walk through today. As usual, anytime you have a question, unmute, say, hang on, Dave, I have a question, and then state your question, and we'll do our best, okay? I'll try to come at it from another direction. One thing I can't deal with is, hey, Dave, I don't get it. And that's binary. I either agree with you or I disagree with you. And since you know you better than I know you, I'll agree with you. Yep, you don't get it. Try to give me a question so that we have somewhere to go. All right, trig compositions. Again, like any other, it's a function happening within another function. If we have f of x and we're going to replace that x with some other function, that's all that is. We replace the x with that function. We perform that function, and that answer then goes to the outer again. So do the inner function first, put the answer from the inner into the outer, and resolve for an answer. So let's take a look. Here I have the arc cosine or cosine inverse of the cosine of negative pi over 4. Now, we've been kind of defining where you can do an arc cosine. Can I do an arc cosine of negative pi over 4? No, I cannot, but that's not what I'm asking. We're asking about the cosine of negative pi over 4, which is perfectly okay. What I want to do is get to where it says arc cosine of a value. Cosine of negative pi over 4, cosine of an angle will give us a value that we can process. First thing we have to do is figure out what the value of cosine negative pi over 4 is. So we're going to set x to the cosine of negative pi over 4. And I drew a picture here. We are falling from the positive x-axis, the 0 radian line. We're falling or rotating by pi over 4 in the negative direction, that is clockwise. And so that drops us into quadrant 4. Well, in quadrant 4, x is positive, y is negative, and the cosine being the first thing, remember it's alphabetic, just like xy is, cosine comma sine. We're going to grab the cosine value of that, square roots of 2 over 2, and plop it into arc cosine, the outer function. So now the question is, what is the arc cosine of square roots of 2 over 2? And now here we have some restrictions. In arc cosine, I can only pull my answer from quadrants 1 and 2. And since it's positive square roots of 2 over 2, that means it's coming, the angle is in quadrant 1. If the value were negative, then we would process through quadrant 1 into quadrant 2 and grab a negative value, but an angle that has a negative value. So cosine inverse of square roots of 2 over 2 is pi over 4. And so here we have our answer. The arc cosine of the cosine of negative pi over 4 is pi over 4. So pay attention where your arcs are leading you, your inverses are leading you. And remember that it's perfectly okay to take an angle in any direction from any quadrant of a normal sine, cosine, tangent, whatever. It's when we have the inverse that we are restricted. All right, so let's review that. I know we talked kind of quickly about it, but let's review where these things are valid, where we can talk, right? So this is regards inverses, right? Sine of theta, if we are going to have an inverse called arcsine or sine inverse, then we have to limit the domain of sine to between negative pi over 2 and pi over 2. So quadrants 1 and 4. The range doesn't change. We're still going from -1 to 1. And that means that our sine inverse, arcsine of some value, I called it x on the last page, let me call it x here. Remember that when we have inverse, our domain and range change places. The x and the y exchange places. So the domain of arcsine is -1 to 1. That's the question we may ask. And the answers will come from an angle in quadrants 1 or 4. That range of possible answers is negative pi over 2 to pi over 2. Cosine, in order to have an inverse, also is limited. Its domain are the first and second quadrants because it's analogous to x, right? So we can go in a normal manner, anti-clockwise. And in quadrant 1, we have all of the possible range of positive answers and go straight into quadrant 2 where we have all of the range of possible negative answers. Cosine inverse flips. I can ask the question regarding the values between -1 and 1. And the answer that I will give will fall on quadrants 1 or 2 from 0 to pi, including, notice the brackets. When discussing tangent, now remember tangent, we have vertical asymptotes now, right? So our domain limited is from negative pi over 2 to pi over 2, and that's because sine is in the numerator, right? So sine is driving where we can look, but since we're up against vertical asymptotes, we won't touch these two values. We can only approach them. And the range of tangent, remember what tangent looks like, is any real number, which again, of course, we cannot be equal to the infinities. That makes arctangent or tangent inverse. It has a domain of any number you want to put in. That's real restricting, right? And a range from negative pi over 2 to pi over 2, but we cannot touch them. And we did a drawing the other day. We said at that 90 degree and negative 90 degree that the value of tangent is undefined because the cosine sine is 1, 0 or -1, 0. Sorry, I said that backwards, 0, 1 or 0, -1. And that would cause division by 0 because y over x would be 1 over 0 or -1 over 0. And of course, that's not allowed. Doesn't matter what math you're in. You can be in calculus 29. You still can't divide by 0. Horrible things happen when you try to divide by 0. Don't do it. Planets crash into their suns. Moons collide. People get married. Horrible things happen when you try to divide by 0. So don't. All right, back to compositions. So let's look at this. Sine of the arcsine of 1/2. Now, the arcsine of positive 1/2 means that the angle that arcsine is referencing has to come from quadrant 1, because we are limited to taking our answers only from quadrants 1 and 4. So the value is positive, it must be coming from quadrant 1. If it was negative, it would be coming from quadrant 4. So the first thing we want to do is the inner function. Sine inverse of positive 1/2 from quadrant 1. And what we're saying is, where is sine of theta equal to 1/2? Well, that's at pi over 6. So then we go to the outer function. And we say, what is the sine of pi over 6? See how this can be really pretty easy? And I'm not sure how she's teaching with you guys. Do you memorize the pi over 6? That's 1/2, right? All right, let's take another. Let's look at cosine of the arc cosine of negative square roots of 3 over 2. All right, now remember, we had to limit cosine's answers to quadrants 1 and 2 because cosine is analogous to x. X is positive in quadrant 1, negative in quadrant 2. So we didn't have to do anything unnatural with the motion through the circle. We go through quadrant 1 for all the positives and continue naturally into quadrant 2 for the negatives. So our inner coming from quadrant 2. Where is cosine theta equal to negative square roots of 3 over 2? Now, we see it's a denominator 6, right? In quadrant 2. So if you're not sure, that's, we can count them off. Pi over 6 is in quadrant 1. 2 pi over 6 is really pi over 3, but that's still in quadrant 1. 3 pi over 6 is the y-axis. That's 90 degrees, pi over 2. 4 pi over 6 is really 2 pi over 3. And of course, that's in quadrant 2. So we've entered quadrant 2 now. 5 pi over 6 can't be simplified. So that's my answer, is 5 pi over 6. But just to go one further, 6 pi over 6 is really pi. So I'm back on the x-axis, of course, the negative x-axis now. So put that into the outer. The cosine of 5 pi over 6 is equal precisely to negative square roots of 3 sitting on 2. Check. Now you're looking at these two going, well, these are different because I'm taking the sine of the arcsine and I'm just getting the number that's already in there. Well, sometimes that's going to happen. So let's explore when that is possible. Doesn't mean you can just blindly go, well, then that's clearly that's a half, because look at the one on the last page. First page didn't work out that way, right? We can say that the sine of the arc sine of a value x will be equal precisely to x. Now here's a new math term for you, IFF, and this means if and only if the value of x lies between and including -1 to 1, which happens to be the domain of arc sine, right? We can say that the cosine of the arc cosine of a value x equals precisely x if and only if, well, we have that same domain on cosine, don't we? -1 to 1 inclusive. Then along comes tangent. It says, I want to be part of this. But that may only happen when we fall somewhere between -infinity and infinity. So yeah, not a whole lot of standards on tangent, arc tangents part. Huh? Now going the other direction, the arc sine of sine of some angle will be equal precisely to that angle if and only if we are where sine is valid to have an inverse. So between -pi/2 and pi/2. The arc cosine of the cosine. So we're going to take the cosine of an angle and then undo it, and it's going to be equal precisely to that angle, but only when we fall between 0 and pi, which is what we've already been playing with, first and second quadrant, right? And then tangent. And tangent, because sine is in the numerator of, you know, how to create tangent, it runs the show. So again, we have to fall between -pi/2 and pi/2, but remember, we're not permitted to be equal to those values because on those values, sine over cosine creates division by 0. So why did we do this? Well, so that we can do the next thing. You ready? Don't have a choice, no.
1 second.
Yep. You're doing the right thing. You guys doing okay with me? I know it's not the same as face-to-face, and I know that she's very, very good, Ms. Luna, but you doing okay? You know, it's okay to interrupt me and ask a question.
Thank you, sir.
I'm Dave. It wasn't even a sir anymore. Good to go?
Yes.
Cool, cool. All right, I'm going to give you a tough one, and then we're going to come back and kind of work through some easier ones, and then we'll go back to a tough one again, okay? So you're going to have fun with this because at heart, you're all puzzle people. You wouldn't have made it this far in math if you didn't have some aptitude for it. So embrace the geek, have fun with it. Let's talk about the sine of the arctangent of u. Now, this leads to some weird conversations because I want to take the arctangent of u, and then some kid always says, why me? No, not you, you. So we get into a whole Abbott and Costello thing. And this is leading up to the question I had earlier about the homework. So here's where this begins. Couple of steps, and if you follow these steps, you're going to walk through this, come out the other end with the correct answer and just feeling on top of the world. So like before, the first thing we need to do is we need to get to sine of an angle, because that's the only thing I can take the sine of is an angle, right? So we're going to set theta to be the arctangent of the value u. So far, so good? All right. Now, we need to get that u alone. There's another part of that awkward conversation. What we're going to do is take the tangent of the arctangent of u. And if I do it to this side, I have to do it to the other side. So we have tangent of theta. And as we discussed, we have to assume it's on the right playing field, right? So tangent and arctangent cancel, and I'm left with u being equal to the tangent of theta. And here's probably the single most important part. We're going to draw a picture. Specifically, we're going to draw a triangle. Now, tangent of theta, remember, is sine over cosine, or y over mx, right? And that would be equal to u over 1. Now, why did we do that? Remember, any number can be written as a rational number, as a fraction. 5 is the same thing as 5 over 1, or 10 over 2, or 20 over 4, okay? So if I need a y and an x, so I simply made u into a rational number. So we might also say that this is the opposite over the adjacent. So opposite the angle is equal to u. Adjacent to the angle is equal to the number 1. And we see that we are missing the radius. Well, surprise, that's part 4. Now, it doesn't matter which side you're looking for. This time it's the radius, but we're always going to start here. R squared is equal to x squared plus y squared. Remember, that's a circle, right? R squared is equal to 1 squared plus x squared. I know 1 squared looks silly, but I'm doing all of the steps so that I can't forget the step when it's important, okay? So that means that R is equal to x squared plus 1 square root. And I know that you're looking going, wait a minute, isn't a square root supposed to be plus and minus? You're right, good for you, but R is always positive because it's a diameter, it's distance, it cannot be negative. And that leaves us our very last step. So I'm going to go back here and label R square root of u squared plus 1. That's the best we can do until someone tells us what u is equal to. And so I can now solve from the picture. Watch how easy this is. Sine of theta is equal to y over r. Y is u. R is the square root of u squared plus 1. And then we're not quite done. You're looking at that going, I can't leave that in the denominator. And you're right. Good for you. So I have to clean it up. So we have u over the square root of u squared plus 1. Oops. Times square root of u squared plus 1. Square root of u squared plus 1, because we can't leave that radical in the denominator, right? And so my final answer is going to be u times the square root of u squared plus 1 over u squared plus 1. And I feel very confident. I'm ready to commit to that answer, so I'm going to put a ring on it. Now, whether you feel confident or not, and if you do, I would be amazed because that's the first time you've seen it. But can you follow the steps? Can you see where the steps are helpful?
Yes.
Lovely. Now let's do some easier ones to help solidify the ideas, and then we'll come back to one of these, right? And these are going to go directly to that homework you were talking about. Is it okay to move forward? All right. Let's look at the tangent of the arc sine of 3 sitting on 5. Now we're going to follow exactly the same steps. Get to tangent theta, because I can only take the tangent of an angle, right? So I'm going to get it into this form so that in step 5, I can simply say, well, tangent is y over x, right? That means that theta is the arc sine of 3 over 5 I'm going to get 3 over 5 alone. And I'm going to do that by taking the sine. Oh yeah, I can do it this way. Sine of the arc sine, 3 over 5. If I do it to that side, got to do it to this side. All right, now, remember that arc sine can only come from quadrant 1 or quadrant 4, right? Well, 3 over 5 is projected as being positive, so it must be in quadrant 1. And so that's how we're going to draw our picture. is from origin. We're going to create this angle in quadrant 1. Right? And we're going to remind ourselves what sine theta is. Sine is y over r, and 3 over 5. That makes 3 on the y, or the opposite. And our radius is equal to 5. And that means that we are hunting for our x. So far, there's practically no way to go wrong, right? All we did was draw out labels. So we want to find x, and we're going to do that by starting with r squared being equal to x squared plus y squared. We can put 5 here and square it. I should put it in parentheses. And we don't know x, we're going to leave that alone, plus 3 squared. So that's 25 minus 9 being x squared, making x equal to 4, right? Positive, because quadrant 1. So now I can come down here and label my x. And now the easiest step of all, solve from picture. Tangent of theta is the opposite over the adjacent, or y over x, and that is simply 3 over 4. So all of that just so that we can say that the tangent of the arcsine of 3 over 5 is equal to nothing other than 3 over 4. All right, so the person that said they had a question on this from the homework, a little better?
Yes, it is. Thank you.
All right, so let's change this and talk about what happens if we're not looking for a positive, but we're looking for a negative. So the only thing we did is I made 3/5 negative. I still have to get to tangent of an angle. I'm going to set angle equal to arcsine of the value. I have to get the value by itself alone. And I'm going to follow the same steps to do that. But my picture is going to change. Because sine, the arcsine is negative in quadrant 4. So when I draw my picture, I'm going to draw it emanating from quadrant 4. Sine of theta is y over r. R is positive. So I have -3 over +5. And I'm going to go searching for x. I'm going to do the same thing. Now it's really important you have the parentheses. It doesn't change your answer, but it does change how you set things up. If you do it wrong, you could be led to give yourself a bad answer. -3 squared, -3 times -3, of course, is +9. So we still have 25 minus 9 being x squared. And x is still going to be +4. In quadrant 4, x is positive, y is negative. And we're still going to solve from the picture. Tangent is still opposite over adjacent. It's still y over x. But now my answer is -3 over 4. All right, so pay attention to where you're drawing your picture. It's either going to be quadrant 1, quadrant 4, or quadrant 2, depending on what you're being asked to evaluate.
Here, on the part where you put x equals positive and y equals negative, on after you put x
In
equals
quadrant
4, yes.
Mhm.
So you're saying in quadrant 4, the tangent x equals positive and y equals negative?
All right, so quadrants 1 through 4, right? Here, x is positive, y is positive, yes. In quadrant 2, x has gone negative, but y remains happy. In quadrant 3, nobody likes being in quadrant 3. And in quadrant 4, x has gone back to being positive, but y remains the downer.
Gotcha, that makes sense.
All right, let's go back to one of those questions about you. Not you, but, you know, you. Let's look at the cosine of the arc sine. And let's just make it fun. Let's go -u. Same steps. I can only ask the cosine of an angle. So angle must be equal to the arc sine of -u. Sine of theta is equal to the sine, the arc sine of negative u now sine is y over r, right? Negative u over positive 1 because r is always positive, right? All right. If arc sine is negative, then we're in quadrant 4, yes? Looking for x. Remember, we start the same way. R squared is x squared plus y squared. You're going to find, I hate memorizing. I don't think you need to memorize anything after your times tables and your 2 special rate triangles. But if you write down your formula every time you're about to use it, you know what's going to happen? You're going to memorize it, but you're going to memorize it in context, right? So that when you hit that situation again, it'll come back to memory. It's not just riding around in your memory like that stuff, like studying for a history test. My wife has a term for that. I love this term. I keep telling her to copyright it. She calls that bulimic learning, because you shove all the information, you regurgitate it on the test, and it is gone forever. You feeling pretty confident now? Same steps, every time. The biggest thing, the single biggest thing is number 3. Draw that picture. Label your triangle. Questions? Pretty much makes sense? I said pretty much. Feeling good? Okay to move forward to the next thing? All right. So I'm going to jump over 3.3 right now because you need a little bit of what's in 3.4 for 3.3 to be workable. So we're going to come back, or Ms. Luna will come back to 3.3, but you need a couple of these IDs to make good substitutions to make 3.3 easier. So let's talk a little bit about some of the identities. And from then we're headed, of course, into proofs, but not today. That's 3.5. By the way, I'm not going to write identities anymore. I'm going to say ID or IDs. All right, you know these. You may not know them by these names, but you know these. We have the reciprocal identities. And you know that the sine of theta is the same thing as 1 over the cosecant of theta. And so it follows that the cosecant of theta is the same as the reciprocal of sine of theta. Cosine theta is the same as the reciprocal, or 1 over secant, making secant 1 over or the reciprocal of cosine. And then we got our buddy tangent, who's always outside the fence, wanting to come in and play. That's 1 over cotangent, or the reciprocal of cotangent. So it's no surprise that cotangent is 1 over tangent, or the reciprocal of tangent. Another one you may not know it by this name, but you know these quotient IDs. That is that these identities come from a ratio of other identities. And we have tangent theta, which is the ratio of sine theta to cosine theta. And cotangent, which comes to us by way of dividing cosine by sine. All right, powers. Now, not power IDs, just powers. Squaring, cubing, any, well, let me say raising to any power. Does not change the relationship. So for instance, sine squared of theta then simply is the reciprocal of, or 1 over cosecant squared of theta. That's all. Or tangent squared of theta is sine squared of theta over cosine squared of theta. That's all. So if you see these powers, as long as they're the same powers, they don't change the relationships at all. All right. Everybody knows about Pythagoras. And from the Pythagorean theorem come Pythagorean IDs. Now that's plural on purpose. There are 3 of them. So quick reminder, Pythagoras said, I guess he's dead, that a squared plus b squared is the hypotenuse squared, right? So the squares of the sides when added will give us the square of the hypotenuse. Well, in a circle, C has become radius, and that brings us to a squared plus b squared is r squared. On a unit circle, r is equal precisely to 1, and that gets us to a squared plus b squared is 1 squared. Also on a unit circle, x is replacing the a, y is replacing the b, and we now say x squared plus y squared is equal to 1, and that's a circle, right? It has a radius of 1, and it's centered on the origin. And finally, on a unit circle, r equals 1, cosine theta being x over r is x over 1, or x. Sine of theta is y over r, or y over 1, or simply y. And that gets us finally to our first Pythagorean. Cosine squared of theta plus sine squared of theta is equal to 1. And that's our first Pythagorean ID. So it doesn't matter what the angle is. You probably saw this on homework. Let's say cosine squared of 42 degrees plus sine squared of 42 degrees is 1. If it's the same angle, square of the cosine, square of the sine will be equal to 1. So here's what's happening. If we have sine squared theta plus cosine squared theta, equal to 1, and I want to get rid of sine squared, then I'm going to multiply sine squared, 1 over sine squared, with sine squared plus cosine squared being, and that's going to give me sine squared over sine squared, cosine squared over sine squared, and 1 over sine squared. We said relationships don't change. So sine squared over sine squared is 1. Cosine over sine is cotangent. They're both squared, so we would say cotangent squared. Put my theta back on here at the end. And 1 over sine is cosecant, so we would say cosecant squared theta. The other one, same thing happens, except we're removing cosine squared. So we have sine squared over cosine squared, cosine over cosine squared, and 1 over cosine squared, giving us 1. Oops, got ahead of myself. Giving us tangent squared theta plus 1 is secant squared. And that's your other two Pythagorean IDs. Now, these Pythagorean IDs come up a lot, okay? So I'm not going to say memorize them, but have them handy, right? You will, over time, memorize them, but do it while you're doing your work, right? If you see something that has a ratio squared, think Pythagoras, go look it up, see if you can make it. All right, the co-function IDs, actually many of you probably already noticed this. Did you notice that the sine and cosine of pi over 6 and pi over 3 are the same numbers, just in the other order? Cofunction is two angles that add up to 90 degrees, or pi over 2. That is, they are complementary angles. Remember that from 8th grade? So the pairs that co-function are sine and cosine. Their reciprocals, cosecant and secant, and the two outsiders, tangent and cotangent. I was going to say 2 pi over 6, but nobody calls it that. So cosine of pi over 6 is square roots of 3 over 2. And the sine of pi over 3 is square roots of 3 over 2. Take a look. Pi over 6 is square roots of 3 over 2, 1/2. Pi over 3 is 1/2 square roots of 3 over 2. Right? They exchange places. Also, we might say that the tangent of, well, that's too easy. Pi over 3 is the same thing as the cotangent of pi over 6. Okay, because pi over 3 and pi over 6 add up to, all right, so how it works. We would say the sine of 90 minus some angle theta is the same thing as cosine of that angle, or cosine of 90 minus angle is the sine of that angle, or we might say the tangent of pi over 2 minus an angle is going to be the cotangent of that angle. You get it? Easy, right? All right, so these are the basic ones that are going to help you to navigate 3.3 a little more easily, because you can take these ideas and substitute them for values that you're trying to equate in 3.3. This is not all of 3.4. You will come back and revisit this and add some more ideas to it, and then you'll begin to do some proofs with it. Any questions on what we talked about today? I love it that you stopped me and asked questions, by the way. Very good. Good on you. Keep it up. Remember, any class you're in, you are the only person advocating for you. If you're ever in a class where the teacher hates questions, doesn't answer them, or worse, makes you feel bad for asking them, stop, get out of that class and get into a class where the teacher invites or at least tolerates questions. All right, you're paying too much money to be here to leave without an education. Any questions? Comments? Complaints? Gripes? Moans? No? I'll be sending these slides and the ones from Tuesday to Ms. Luna. And when she gets back, I'm sure she will post them up onto Blackboard, and the recording that we've been making should be posted under Panopto. For those of you that are just gluttons for punishment, you want to hear my voice again. You've been absolutely wonderful, and I really appreciate that you've come out. Thank you. Any questions from anyone? I release you. If you don't want to ask a question or don't want to hear other people's questions, you're released. If you wanted to ask a question, or there's a follow-on question to something that was asked earlier, please hang out and we'll chat.
Sir, do you teach calculus?
I have taught calculus, but not here at the UTSA. The good news is calculus is very, very easy. No, truly.